Hello everyone. Let's start the fifth part of the optimum driving and braking force distribution curve and center of gravity. I will explain an overview of the optimum front and rear axle non-dimensional driving and braking force distribution curve, and then explain the basic theory and the process of deriving the mathematical formulas needed to draw this curve. I will explain how to calculate the slope at the origin in the non-dimensional force coordinate system and its relationship to the location of the center of gravity. Based on this, I will explain how to draw the optimum non-dimensional driving and braking force distribution curve for the front and rear axles using the Excel program. That's all for this video. In the next video E0008B, I will explain how to calculate the slope and intercept related to the constant friction coefficient mu line during driving and braking, and then draw the line using the Excel program based on the derived mathematical formulas. Finally, I will summarize the contents of this video. The structure of this video is to first give you an overview of the non-dimensional driving and braking force distribution curve, and then explain the details. I have a quiz for you. Which of the following is true when driving or braking? All cars have the same weight and wheelbase. The higher the center of gravity, the more weight transfer. The lower the center of gravity, the more weight transfer. The height of the center of gravity has nothing to do with weight transfer. Choose one of these. In the last video, we learned that when there is sufficient friction between the road surface and the tires, there is tilting acceleration, which is the front axle lifting off the ground during driving, and tilting deceleration, which is the rear axle lifting off the ground during braking. These two accelerations are important characteristics for drawing driving and braking force distribution curve, so let's review them. Since deceleration is negative acceleration, from now on, unless necessary, we will call both accelerations. In a four-wheel drive vehicle, if the driving force of the front tires is Fxf, the driving force of the rear tires is Fxr, and the vehicle acceleration is a, then their relationship can be expressed as equation 1. If both sides of equation 1 are divided by mg, we can make it non-dimensional and obtain equation 2. As explained in the previous video H0007, Optimum Driving and Braking Force Distribution Curve and Center of Gravity Part 2, the non-dimensional representation of the front axle driving force can be expressed as equation 3. The non-dimensional expression for the rear axle driving force can be expressed as equation 4, and in the equation 3, the first term in the parentheses on the right side represents the driving force based on front static vertical load, and the second term represents the dynamic load due to acceleration A. Similarly, the non-dimensional expression of the rear axle driving force can be expressed as equation 4, where the first term in the parentheses on the right side represents the driving force based on rear static vertical load, and the second term represents the dynamic load due to acceleration A. Here, if the front axle friction coefficient and the rear axle friction coefficient have the same value as shown in equation 5, the front axle driving force can be expressed by equation 6, and the rear axle driving force can be expressed by equation 7. Since the acceleration has a positive value when driving and a negative value when braking, equation 6 and equation 7 can be used for both driving and braking. Let's first look at tilting deceleration. Since the braking limit occurs just before the rear axle leaves the ground, the rear wheel braking force becomes 0 and can be expressed by equation 8. By substituting this value into equation 7, we can obtain the result of equation 9, which represents the g unit of the tilting deceleration. If we substitute equation 9 into equation 6, we can obtain equation 10. Equation 10 obviously means that the front wheels handle the entire braking force. The tilting acceleration can also be obtained in the same way. Since the acceleration limit occurs just before the front axle leaves the ground, the front wheel driving force becomes 0 and can be expressed by equation 11. By substituting this value into equation 6, we can obtain equation 12, which represents the g-unit of the tilting acceleration. If we substitute equation 12 into equation 7, we can obtain equation 13. Equation 13 obviously means that the rear wheels handle the entire driving force. Now that we have obtained the tilting acceleration and tilting deceleration for driving and braking, let's find the optimum acceleration distribution line. Let's understand the meaning of the non-dimensional optimum front and rear axle driving and braking force distribution curve. The vertical axis of the graph here represents the non-dimensional value of the front axle driving force 2Fxf divided by mg, and the horizontal axis represents the non-dimensional value of the rear axle driving force 2Fxr divided by mg. The coordinate system composed of these two axes that intersect at right angles will be called a non-dimensional force coordinate system. In addition, for the convenience of explanation, the non-dimensionalized front axle driving force will be called front wheel driving force, the non-dimensionalized rear axle driving force will be called rear wheel driving force, and the non-dimensionalized front axle braking force will be called front wheel braking force, and the non-dimensionalized rear axle braking force will be called rear wheel braking force. In addition, the non-dimensionalized optimum front and rear axle driving and braking force distribution curve will be called optimum force distribution curve. The green graph shows the optimum force distribution curve on a non-dimensional force axis when the front and rear wheels have the same friction coefficients in a four-wheel drive vehicle. Above-mentioned green graph here is a non-dimensional representation of the driving and braking force when the front and rear wheels have the same friction coefficient in a four-wheel drive vehicle. The non-dimensional forces on the front and rear axles can be expressed as in equations 6 and 7, as explained above. If equations 6 and 7 are expressed together using equation 2, the green graph is created. Any point in the area excluding the green line represents non-dimensional force when the friction coefficients of the front and rear axles of the vehicle are different. However, in any case, the sum of the non-dimensional front driving force and non-dimensional rear driving force in the acceleration area of the first quadrant must not exceed the tilting acceleration, and the sum of the non-dimensional front braking force and non-dimensional rear braking force in the braking area must not exceed the tilting braking in terms of their absolute value. Here, the first quadrant represents the optimum driving force distribution curve, and the third quadrant represents the optimum braking force distribution curve. For example, the figure here shows an optimum force distribution curve for a vehicle with center of gravity height, wheelbase, distance from center of gravity to front axle LF, and distance from center of gravity to rear axle LR, as shown in the specifications on the lower right. The point P shows that when the vehicle accelerates at 1.5 g-unit, a non-dimensional driving force of 0.55 g-unit occurs on the front axle and 0.95 g-unit occurs on the rear axle. Another point Q indicates that when the vehicle decelerates at -1.1 g-unit, a non-dimensional braking force of -0.85 g-unit is generated at the front axle and -0.25 g-unit at the rear axle. The distribution curve can show the fore and aft position of the center of gravity. As shown in the figure, if the tilting acceleration is greater than the absolute value of the tilting braking, it means that the center of gravity is closer to the front axle than the rear axle, and if the absolute value of the tilting braking is greater than the tilting acceleration, it means that the center of gravity is closer to the rear axle than the front axle. The slope at the origin of the optimum force distribution curve is determined only by where the center of gravity is located along the longitudinal direction, as shown in equation 16. Equation 16, which represents the slope, is explained later. The slope at the origin is simply the distance from the center of gravity to the rear axle divided by the distance from the center of gravity to the front axle. Therefore, as the distance from the center of gravity to the rear axle becomes relatively longer than the distance to the front axle, the slope becomes steeper toward the vertical axis. In the extreme case where all the weight is concentrated on the front axle, the rear axle weight becomes 0, and the value of the distance LF from the center of gravity to the front axle becomes 0, so the slope increases infinitely large and becomes the vertical axis. In this case, braking is impossible, so all the green graphs in the third quadrant are reduced to one point, the origin. Conversely, as the distance from the center of gravity to the front axle becomes relatively longer than the distance to the rear axle, the slope becomes flat toward the horizontal axis. In the extreme case where all the weight is concentrated on the rear axle, the front axle weight becomes 0, and the value of the distance LR from the center of gravity to the rear axle becomes 0, so the slope becomes infinitely small and becomes a horizontal axis. In this case, since acceleration is impossible, all the green graphs in the first quadrant are reduced to one point, the origin. On the other hand, as shown in equation 16, if the length from the center of gravity to the front axle and the length to the rear axle are the same, the slope at the origin becomes 1. Here we will see how the constant friction coefficient lines are represented in the driving force domain of the nondimensional force coordinate system. The constant friction coefficient line is represented by a straight line. The constant front axle friction coefficient line passes through the tilting acceleration, and the constant rear axle friction coefficient line passes through the tilting braking. All straight lines shown here represent constant friction coefficient lines for the front and rear axles in the first quadrant of the nondimensional force coordinate system representing the acceleration domain. For example, point P represents the point where the friction coefficient of the front axle is 0.5 and the friction coefficient of the rear axle is 0.75. The point where the horizontal line passing through point P intersects the vertical axis represents the front wheel driving force, and the point where the vertical line passing through point P intersects the horizontal axis represents the rear wheel driving force. The total driving force is the sum of these two. To help you understand, let me explain one more point. Point Q represents the point where the coefficient of friction of the front axle is 0.25 and the coefficient of friction of the rear axle is 1. The point where the horizontal line through point Q intersects the vertical axis represents the front wheel driving force, and the point where the vertical line through point Q intersects the horizontal axis represents the rear wheel driving force. The total driving force is the sum of these two. Here we will see how the constant friction coefficient lines are represented in the braking force domain of the nondimensional force coordinate system. As before, the constant friction coefficient line is represented by a straight line. The constant front wheel friction coefficient line passes through the tilting acceleration, and the constant rear wheel friction coefficient line passes through the tilting braking. All straight lines shown here represent constant friction coefficient lines for the front and rear axles in the third quadrant of the nondimensional force coordinate system representing the braking domain. For example, point P represents the point where the friction coefficient of the front axle is 0.5 and the friction coefficient of the rear axle is 0.25. The point where the horizontal line passing through point P intersects the vertical axis represents the front wheel braking force, and the point where the vertical line passing through point P intersects the horizontal axis represents the rear wheel braking force. The total non-dimensional braking force is the sum of these two. To help you understand, let me explain one more point. Point Q represents the point where the coefficient of friction of the front axle is 1 and that of the rear axle is 0.5. The point where the horizontal line through point Q intersects the vertical axis represents the front wheel braking force, and the point where the vertical line through point Q intersects the horizontal axis represents the rear wheel braking force. The total non-dimensional driving force is the sum of these two. Here, we will draw the entire acceleration and braking force constant lines in the nondimensional force coordinate system. First, In the acceleration domain, the constant entire acceleration force in the first quadrant means that the acceleration is constant in the previously obtained equation 2. Therefore, when the vehicle accelerates at 1 g-unit, the line where the entire acceleration is constant can be expressed by equation A, which is represented by the light blue straight line in the figure. In addition, when the vehicle accelerates at 0.5 g-units, the line where the entire acceleration is constant can be expressed by equation B, which is represented by the blue straight line in the figure. Next, in the braking section, when the vehicle brakes at -1 g-unit, the line where the entire braking force is constant can be expressed by equation D, which is represented by the red straight line in the figure. In addition, when the vehicle brakes at -0.5 g-units, the line where the entire braking force is constant can be expressed by equation C, which is represented by the dark red straight line in the figure. This concludes the outline of the optimum force distribution curve, and I will now explain in detail the theory and mathematical formulas required to represent them in a graph. Let's take a closer look at the overall overview we've looked at so far. First, let's calculate the slope at the origin. The slope at the origin can be obtained from equations 6 and 7, which were explained in part 2 of the previous video E0008A optimum braking and driving force distribution curve. Since the slope at the origin is the increase in the front axle force with respect to the increase in the rear axle force at the origin, it can be expressed as the increase in the front axle force divided by the increase in the rear axle force, and the slope at the origin can be obtained by finding the limit value when the acceleration converges to 0 in equation 14. Therefore, the slope at the origin can be expressed as equation 14. If we rearrange equation 14, only the first term of the numerator and denominator remains, so the final result can be expressed as equation 15. Therefore, the slope at the origin of the distribution curve is the length from the center of gravity to the rear wheel divided by the length from the center of gravity to the front wheel. If we substitute the data of LF and LR for the example vehicle shown in the table into equation 15 and calculate it, we can obtain a slope of 1.5 as in equation 16. Looking at this final result, when LR becomes 0, the slope becomes 0. And since 100% of the center of gravity is on the rear wheels, acceleration is impossible and only braking is possible. Therefore, the driving force distribution curve of the first quadrant is reduced to 1 point and located at the origin. Conversely, when LF becomes 0, the slope becomes infinite, and since 100% of the center of gravity is on the front wheels, braking is impossible and only acceleration is possible. Therefore, the braking force distribution curve of the third quadrant is reduced to 1 point and located at the origin. Let's use the above equations 6, 7, and 1 to create a graph of the optimum force distribution curve using Excel. First, in order to determine the data range, we calculate the above tilting braking and tilting acceleration in g-units. All g-unit values between these two values represent all accelerations and decelerations that can occur when all axles of the vehicle are attached to the ground. G-unit values outside this range represent a state where one of the vehicle's axles is off the ground, so there is no need to analyze them. By substituting the distance LF from the center of gravity to the front axle and the height h of the center of gravity into the above equation 10 to obtain the tilting braking, we can calculate the value of -2.57, represented by U. Next, by substituting the distance LR from the center of gravity to the rear axle and the height h of the center of gravity into the above equation 13 to obtain the tilting acceleration, we can calculate the value of 3.86, represented by VE. Enter the calculation formula of equation 10 into the red cell A02 of the first column of the Excel sheet to calculate the value A. Enter -2.3 into the cell A03 directly below it, and increase the G-unit value by 0.2 from the cell A04 directly below it to A33. The smaller the increase, the more detailed the graph can be. Next, enter equation 13 into cell A34 to calculate the tilting acceleration of 3.86. Next, enter the wheelbase of 2.805 into cell B02 and copy this cell and fill in cell B34 with the same value. In the same way, enter the center of gravity height CGH in column C, the distance from the center of gravity to the front axle LF in column D, and the distance from the center of gravity to the rear axle LR in column E to fill in the corresponding cells. Next, enter the equation for dividing E02 by B02 in cell F02. Enter the equation for dividing D02 by B02 in cell G02, and then enter the equation for dividing C02 by B02 in cell H02. Enter the equation for multiplying F02 by A02 in cell I02, and then enter the equation for multiplying H02 by the square of A02 in cell J02. Continuing to enter the equation for subtracting J02 from I02 in cell K02, you can obtain the non-dimensional acceleration of the front axis, which is the value of equation 6. Next, enter the equation for multiplying G02 by A02 in cell L02. Afterwards, if you input the formula for adding the L02 cell and the J02 cell to the M02 cell, you can obtain the non-dimensional driving force of the rear axle, which is the value of formula 7. Continuing, if you copy the formulas of all cells from the F02 cell to the M02 cell and paste them all, starting from the row from the F03 cell to the M03 cell, to the row from the F34 cell to the M34 cell, you can get the result shown here. Finally, by selecting the data in the column K and the column M and drawing a graph, you can obtain the optimum force distribution curve, which we saw before. Let's find the maximum driving force of the front wheels in a four-wheel drive vehicle. In acceleration, the load at the front wheels is transferred to the rear wheels, so when acceleration occurs, the vertical load of the front wheels pressing down on the ground decreases. Accordingly, when the vehicle acceleration exceeds a certain acceleration level, the front wheel driving force decreases. As previously discussed, the front wheel driving force can be expressed by equation 6. At the moment when the front wheel driving force is maximum, the derivative of equation 6 with respect to acceleration becomes 0. Therefore, equation 17 can be obtained. If equation 17 is solved for g units, equation 18 can be obtained. If the g unit value of equation 18 is substituted into equation 6, equation 19 can be obtained, and this result represents the maximum driving force of the front wheels. As shown in the figure, this value is 0.579, which is the vertical coordinate of point A. At this time, the horizontal coordinate of point A represents the rear wheel driving force when the front wheels produce maximum driving force. The equation for this can be obtained by substituting the g-unit expression of equation 18 into equation 7, as shown in equation 20. In this example, the horizontal coordinate of pointer can be obtained as 1.351 by substituting the data in the table and calculating it, as shown in the figure. To summarize the results, the non-dimensional maximum driving force of the front wheels in the example vehicle is 0.579, and the non-dimensional driving force of the rear wheel is 1.351. Next, let's find the maximum braking force of the rear wheels in a four-wheel drive vehicle. In braking, the load at the rear wheels is transferred to the front wheels, so when braking occurs, the vertical load of the rear wheels pressing down on the ground decreases. Accordingly, when the vehicle deceleration exceeds a certain deceleration level, the rear wheel braking force decreases. As previously discussed, the rear wheel braking can be expressed by equation 7. At the moment when the rear wheel braking is maximum, the derivative of equation 7 with respect to acceleration A becomes 0. Therefore, equation 21 can be obtained. If equation 21 is solved for g units, equation 22 is obtained. If the g-unit expression of equation 22 is substituted into equation 7, equation 23 can be obtained, and this result represents the maximum braking force of the rear wheels. As shown in the figure, this value is minus 0.257, which is the horizontal axis coordinate of point B. At this time, the vertical axis coordinate of point B represents the front wheel braking force when the rear wheels produce maximum braking force. The equation for this can be obtained by substituting the g-unit expression of equation 22 into equation 6, as shown in equation 24. In this example, if the vertical axis coordinate of point B is calculated by substituting the data in the table, it can be obtained as minus 1.029, as shown in the figure. To summarize the results, the non-dimensional maximum rear wheel braking force in the example vehicle is minus 0.257, and the front wheel braking force at this time is minus 1.029. So far, we have obtained the various characteristic values of the optimum force distribution curve, and we can display them all at once as shown here. The green curved line in the first quadrant represents the optimum driving force, and the green curved line in the third quadrant represents the optimum braking force curve. In order to draw the optimum distribution force curve of the example vehicle, we calculated the upper and lower limits of the g-unit. The upper limit of these is the tilting acceleration, and the lower limit is the tilting braking. Next, we found the slope from the origin. Continuing, we obtained the vertical axis coordinate of point A, which represents the maximum non-dimensional driving force of the front wheels during acceleration, and at this time, we obtained the horizontal axis coordinate of point A, which represents the non-dimensional driving force of the rear wheel. In addition, we obtained the horizontal axis coordinate of point B, which represents the maximum non-dimensional braking force of the rear wheels during braking, and at this time, we obtained the vertical axis coordinate of point B, which represents the non-dimensional braking force of the front wheels. The entire acceleration or braking force constant lines, shown in blue in the figure, are also explained. Let's find the answer to the quiz. Which of the following is true when driving or braking? All cars have the same weight and wheelbase. If the wheelbase is the same, the higher the center of gravity, the more weight transfer. If the wheelbase is the same, the lower the center of gravity, the less weight transfer. The height of the center of gravity is directly related to the weight transfer. Therefore, the answer is number 1. The higher the center of gravity, the more weight transfer. Let's summarize what this video covered. I explained the relationship between tilting acceleration and tilting braking and the center of gravity. The tilting acceleration increases as CG gets lower and closer to the front axle. The tilting braking increases as CG gets lower and closer to the rear axle. If the tilting acceleration is greater than the absolute value of the tilting braking, CG is closer to the front axle than the rear axle. If the absolute value of the tilting braking is greater than the tilting acceleration, CG is closer to the rear axle than the front axle. We calculate the slope at the origin on the non-dimensional optimum force distribution curve. When the vertical axis of the optimal force distribution curve is the front wheel non-dimensional force and the horizontal axis is the rear wheel non-dimensional force, slope at the origin is the distance from CG to the rear axle divided by the length from CG to the front axle. Slope at the origin is determined by the longitudinal position data of CG. Slope at the origin decreases as the length from CG to the front axle becomes longer than the length to the rear axle. Slope at the origin increases as the length from CG to the rear axle becomes longer than the length to the front axle. If the length from CG to the front axle and the length to the rear axle are equal, the slope at the origin is 1. The method for obtaining the maximum front-wheel driving force has been explained. In acceleration, the load at the front wheel is transferred to the rear wheel. Accordingly, when acceleration occurs, the front wheel vertical load pressing down on the ground is reduced. Therefore, when the vehicle acceleration exceeds a certain acceleration level, the front wheel driving force is reduced. The maximum driving force occurs at the front wheel when the derivative of the front wheel driving force equation with respect to the acceleration A is 0. Using this, the maximum front wheel driving force and the corresponding rear wheel driving force can be obtained. The method for obtaining the maximum rear wheel braking force has been explained. In deceleration, the load of the rear axle is transferred to the front axle. Accordingly, when braking occurs, the rear wheel vertical load pressing down on the ground is reduced. Therefore, when the vehicle deceleration exceeds a certain deceleration level, the rear wheel braking force is reduced. The maximum braking force at rear wheel occurs when the derivative of the rear wheel braking force equation with respect to the deceleration A is 0. Using this, the maximum rear wheel braking force and the corresponding front wheel braking force can be obtained. If you watch the previous videos, you can learn about various fields of automotive knowledge and enjoy a more in-depth understanding of future videos. In the last video, E0008A, Optimal Braking and Acceleration Distribution Diagram and Center of Gravity Part 3, I explained the importance of lowering CG height with practical example. Lowering CG height is the only way to improve both of acceleration and braking performance. Recently, in my video H0007, Optimal Braking and Acceleration Distribution Diagram and Center of Gravity Part 4, I explained how the optimal braking and acceleration distribution diagram changes depending on the location of the center of gravity. The following video is the second half of the fifth part of the optimal braking force and acceleration force distribution diagram and center of gravity. I will explain how the four types of diagrams representing constant friction coefficients during acceleration and deceleration appear in the nondimensional front and rear wheel driving and braking force coordinate system using mathematical formulas and diagrams. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you at next videos. Goodbye, guys.